Have you ever wondered why in derivatives pricing we use continuous compounding when actual bond rates are always discrete? Or if you have not heard of derivatives at all, have you ever done a depreciation model under straight line method? Have you come across a scenario where you have huge depreciations and negative fixed assets? Why do these things happen? Well, that and a little bit more is what we're going to discuss in this vlog. In the definition of financial modeling, I told you that financial models are represented as mathematical equations that are derived either through structural relations, which is using theory, or statistical relations, which is by observing empirical data. But an important point to note is that even when you have a theory, it is good to cross-check whether the ground level situation works as per theory. Same way, if your empirical data suggests a relationship, it is good to apply a little bit of common sense and see whether the relationship really can be true. Now, a lot of models miss this important point. I'll give you some examples. Sometimes we model capital expenditure as a percentage of sales. Now, I can come up with a broad theoretical link between capex and sales because capex is an outflow and outflow depends on inflow and inflow is your sales. So yes, there is some bit of relationship. But if I'm going to take capex as an X percentage of sales, let's say 5%, is there a theory that backs this? If there is no theory, then what do I do? I'll have to rely on empirical data. But what if empirical data does not give a proper relationship? What if I look at the empirical data and I notice that my capex and sales have no real relationship at all? Can I still use it? The answer is a big no. But what I come across is sometimes analysts, because they tend to use capex as a percentage of sales in all other companies, they end up using it in this case as well, even though there is really no relationship.
So let me explain that to you with this example. So here I have the revenue and capex of Starbucks plotted, and what I notice is that the company's capex to revenue ratio has been very consistent around 6.7 to 7.74%. The average is 7.03 and the coefficient of deviation is 0.06, which is very good. And even the 95% confidence interval is between 6.6% to 7.4%. So here, if I decide to use this relationship between capex and revenue, that's probably good. But it working for Starbucks doesn't mean it should work for every other case. Let's now look at another player in the same industry, Coffee Day Enterprise. So here when I compare the data point, the capex to revenue ratio doesn't look as smooth as what it was in the other case. It's fluctuating anywhere between 11% to 17% and the coefficient of deviation is around 0.17, which is not bad, still not great. And our 95% confidence interval is far wider, between 12.3 to 16.9. So perhaps here if we are going to use capex to revenue ratio, the relationship is pretty doubtful. In some other case it could be outrightly wrong. Let's look at Tesla. The same ratio for Tesla, if you look at it, wavers anywhere between 13.75% to 43.7%. And the coefficient of deviation is very high at 0.4. And if I look at my 95% confidence interval, it's between 18.8% to 42.3. So what we realize is that the capex to revenue ratio gives us a good fit in case of Starbucks, but is absolutely useless in case of Tesla.
Now, if your equation is not backed by theory and neither supported by empirical evidence,
then your equation is just plain wrong.
But sometimes we have theory. The theory alone is not enough. Let me now talk to you about the depreciation modeling example to clarify this. Most companies follow straight line method of depreciation, in which depreciation is calculated at a fixed rate on the original purchase price of an asset. If the company follows straight line method, that gives us a fair enough reason to model depreciation under the same method in our financial models as well. Right? Fair enough, that's a good point. But most often when you model depreciation under straight line method, what you notice happens is that as you extend it across the time, you see depreciation rates get higher and higher and your fixed asset value goes negative. Why does that happen? Because we don't have disposal data, and when you don't factor in disposals, you continue to charge depreciation assets that should have actually been disposed long ago. Now this is an issue that most analysts would face when they are building models under straight line method. What do they do in that case? They end up doing either of the two things. One, play around with your depreciation rate, reduce it a little bit so that at least in your forecast horizon, these weird numbers don't appear. Or you create logic under which there's a hard stop where depreciation stops getting calculated if your asset value falls below a level. Now here is my question. Is there any theory or empirical evidence that suggests that your depreciation rate will go down in future? Or that for a going concern, depreciation will come to a hard stop in future? Now these are important elements that you have to consider before building a financial model. I have a separate chapter dedicated to depreciation in my foundation course. Once that's ready, I'll let you know. But for now, I'll just give you a quick solution. What I would suggest is check whether in the past, if we had modeled depreciation under written down value method, whether the number we would have got would have been more or less in line with straight line method. If a company has large number of assets spread across aging, this is most likely to happen. If this condition is satisfied, I would say better model depreciation under written down value method. You're wondering, now how can I model depreciation under written down value method when the actual structural requirement is to model it under straight line method, right? Now let me take you back to the first question I had asked. Why do we use continuous compounding in derivative pricing when the actual compounding is always discrete? The answer is mathematical convenience. Sometimes in derivatives pricing you will have to use calculus. So if I have an equation of the form y equals 1 plus r power n, and if I have to find its derivation, well, it's going to be pretty difficult. As far as I am concerned, it's almost impossible for me. But on the other hand, if I have y equals e to the power rn, I know its derivation. It is simply n into e to the power rn. So using continuous compounding in place of discrete compounding helps me find a solution. Of course, the solution is approximate, but it's still a solution. So sometimes when you're building a financial model, we may have to use a different form or a different approach if it makes it mathematically viable for us to do a calculation and gives an outcome that is within a fair level of approximation.
So what are the key takeaways that I want you to have? First one is that before using any equation, check whether the relationship between the variables are validated by theoretical relationship between them, preferably and at least or the empirical behavior of the variables. Second thing is, if it is not mathematically viable to replicate the underlying structural relationship as it is, think for an alternative approach that makes it mathematically viable and yet produces an outcome that is approximately closer to the actual outcome. So to put it in a nutshell, whenever you are wondering how to model a particular variable, seek for the right equation rather than going for the easiest formula.
These things should be part of the discourse, and they are part of discourse, but within certain communities, among academicians or among quantitative modelers, not among the other practitioners. Why is it? Because among other practitioners, the prominence rather goes towards spreadsheets rather than mathematics. Now, because of giving over prominence to spreadsheet instead of mathematics, practitioners have created too much complication of situation that have far simpler solution. What are those? Well, we'll talk about it in the next episode. So until then, see you and take care.